When a developer types "fix the failing tests" into a terminal, they are handing over control of their local environment to an AI. But before a single line of code is edited, that text prompt must navigate a highly structured, recursive computational pipeline. We're looking at Qwen Code. This is Alibaba's terminal coding agent, built as a TypeScript fork of Google's Gemini CLI and retargeted specifically to run the Qwen model family, defaulting to Qwen 3.7 Max. Model weights and prompt engineering provide the raw capability, but harness engineering provides the actual utility. This is the architecture surrounding the model, turning a probabilistic text generator into a system that can take concrete actions. To understand how production agents actually work, we have to discard the idea of a simple top-level while loop. Instead, we are going to trace a single prompt through Qwen Code's unique 6-stage data flow. This diagram shows the entire system topology. A prompt enters a central hub and routes through 6 distinct stages of execution, validation, and memory management before it can surface a result. The shape of this loop determines how a raw language model is scaled up into an observable, bounded production pipeline. As we zoom in on the central hub of this topology diagram, the prompt hits the outer driver. This is merely the surface layer, whether it's a headless server, a terminal user interface, or an IPC bridge. All of these surfaces pipe the request into a single generator function called sendMessageStream. Notice how the central node creates a subloop within itself. Qwen Code does not rely on a traditional while loop to keep the agent running. Instead, sendMessageStream is a recursive generator. It uses yield star delegation to continually call itself. Inside a single execution of this generator, a function called turn.run processes exactly one streamed call to the large language model. The output of that turn is then immediately fed back into the start of the recursion. With each recursion, the system decrements a hard budget limit. By default, the max turns constant caps the generator at 100 continuous cycles. Before the stream can even begin, the packet must pass 3 distinct guards: a session turn cap, the per recursion budget, and a strict context window limit. If any of these are exceeded, the generator forces an exit. By utilizing a recursive generator instead of an explicit loop, the execution logic is completely decoupled from the user interface. A single core engine reliably powers any input surface. Once the model receives the prompt, it will likely request to take action, emitting intent to use tools like readFile or run shell command. Looking at this diagram, the packet enters the tool registry. This is a sprawling surface area. Qwen Code ships with roughly 60 built-in tools, a 35-tool computer use suite, and dynamic endpoints for model context protocol servers. Loading every capability at once would strain the system. To mitigate this bloat, the registry is lazy. It instantiates and loads only what is permitted and enabled for the current specific context. To route these requests, the core tool scheduler gathers the model's tool calls and dispatches them in batched turns, processing validation, approval, and execution in parallel where possible. Beyond standard file and shell operations, this stage houses the system's primary differentiator over its Gemini CLI origins: skills. Dedicated curator and learn skill subagents constantly rewrite and expand the skill set, ensuring capabilities self-improve rather than remaining static. The system also integrates MCP, or Model Context Protocol. It operates strictly as a client, deliberately bypassing any .mcp.json server configuration that has not received explicit user approval. Qwen Code prioritizes a high-breadth capability design. It relies heavily on lazy loading and batched execution to handle its extensive action surface without collapsing at runtime. Before a batched tool can execute, the request hits a hard security boundary. This diagram visualizes the evaluate permission flow, where every call is intercepted. The system categorizes operations into a 5-mode approval system. The agent runs in plan, default, auto-edit, auto, or YOLO mode, determining the level of human intervention. In YOLO mode, almost all guardrails are dropped. The system auto-approves executions with exactly one hard-coded exemption. It will never bypass the Ask User Question tool, ensuring the harness maintains a path for human clarification. When operating in auto mode, the request faces a multi-layered filter. Notice these 2 rigid layers scanning the packet. These represent the deterministic security layers. checking operations against a safe allow list, and explicitly stripping out known dangerous rules like destructive shell commands. But the final tiebreaker for auto mode is this third, porous layer. This is an LLM classifier. The harness asks a language model to decide if the pending tool call is safe. If an adversarial instruction enters the terminal output, it can manipulate this classifier into labeling a destructive command as safe. This creates a vulnerability inherent to any system that uses an LLM as a security tiebreaker. Because this classifier is a soft boundary, the system's defense against catastrophic execution ultimately relies on the strength of its deterministic rules, rather than programmatic OS-level sandboxing. Once a tool executes, how does the harness actually know if the directive to fix the failing tests was successful? In Qwen Code, there is no programmatic eval suite running in the background. There is no internal linter daemon checking the output against a strict test matrix. Instead, verification is prompt level. The system relies on a verify standards mandate hard-coded into the system prompt. It tells the model to run the project's shell tests, read the terminal output, and report failures back to the user faithfully. Relying on the model to grade its own homework requires a concrete safety net. In this visual, the FileHistoryService is taking per-turn snapshots of the file state, archiving the entire directory before the LLM makes an edit. If the prompt mandate fails and the model writes destructive code, this snapshot and rollback mechanism is the only true mitigation for the blast radius of the auto and YOLO execution modes. As the turn concludes, the system prepares to feed data back into the recursive loop for the next iteration, but it cannot feed an infinite log of terminal output back into the context window. Memory is split into two tiers. Looking at the bottom level of this diagram, Tier 2 is an active pipeline. Here, data is continuously extracted, recalled, and occasionally explicitly forgotten through a dedicated eviction script. Conversely, the top level represents Tier 1 memory. This consists of hierarchical context files, like a Qwen.md file sitting in the project directory. To manage the volume of data across these tiers, Qwen Code deploys dual compaction. It runs a full compression algorithm alongside a micro-compaction pass that specifically clears out old, bulky tool media. This dual compaction isn't running constantly. It is triggered by circuit breakers tied directly to a session token cap, stepping in only when the context window reaches capacity. But there is an architectural flaw in Tier 1. While Tier 2 actively evicts data, there is no automated pruning path for those hand-edited context files in the project root. This creates a zombie memory risk. Stale directives inside Qwen.md persist across sessions indefinitely, permanently consuming tokens until a developer manually deletes them. Context engineering, the precise mechanism of how memory is pruned, compacted, and injected, acts as the absolute bottleneck. It dictates exactly what the model can see when the next turn begins. Zooming back out to the full system topology, we can see how this single central loop powers broader platform capabilities. Because the generator loop is isolated from the UI, an ACP bridge simply wraps it, exposing the entire agent over HTTP and IPC as a service. The exact same data path is routed to instant messaging channels, allowing a developer to query the agent through DingTalk or Telegram. A dedicated cron scheduler connects to the outer driver, turning a local terminal script into a recurring autonomous system. The ceiling on this autonomy is defined by durable goals. The loop will run continuously to solve complex tasks, but it is hard-coded to stop on evidence exhaustion, preventing infinite runaway execution loops. Operating at this scale exposes specific architectural compromises. The most prominent gap is environmental. There is no hard OS runtime sandbox. The shell operations run with ambient user privileges, relying entirely on logical worktree isolation. We also carry the vulnerability of the soft auto classifier, the total reliance on prompt mandates instead of programmatic evals, and the zombie memory risk of Tier 1. Building a capable autonomous platform depends on the recursive engineering, batched tools, and file rollbacks, as much as it does on model logic. Defining a production agent means understanding exactly where those boundaries lie.